Hi everyone, welcome to the MagNetZ today from the team. I'm really happy to have today Douwe from Utrecht University presenting towards building high-resolution apparent polar wonder paths. Please, Douwe, take it up. The floor is yours.
Thank you very much, Anita. Thanks all for joining and for for listening to what I'm going to tell you. For those of you who were at the Magic meeting 3 years ago in San Diego, you will recognize a few things because this talk builds on from what we did there. And what I will discuss today is so as you might know, I'm in the business of making plate tectonic reconstructions and paleogeographic reconstructions, and paleomagnetism is the only way to quantify that. And I think already when I was a postdoc with Cor Langerijs somewhere in the early Pleistocene, I started to worry and wonder why I was doing the statistics the way I was doing it. And because Cor said, because that's the way we do it, I started to digging a little bit into it. My big problem is that I'm a worthless mathematician, so I need smarter people than me. And I found one in the form, for instance, of Bram, who you see here on the picture, to help me do that, and Martijn Dane back in the day to help me do that. And I will. We made some progress. You may have seen a few papers on this subject in the last years, but I'm still not quite happy where we are. And in this talk, I would like to give a bit of a dream where I think we should be going. But first to the problem. Rosa de Boer, who just finished her PhD here in Utrecht, was so friendly. I also cannot draw, so I also asked somebody to draw for me. Rosa de Boer made this very nice cartoon about paleomagnetism that is carrying plate tectonics and is carrying paleogeography, but is riding on the square wheels on square wheels of statistics right now, which is the analogy that I hope I will convince you about and then give some direction for the future. This is a recent version of the paleogeographic reconstructions that we made that is now behind the new version of paleolatitude.org. And as you all know, the way all of these continents and oceans are displayed on the planet rely heavily on paleomagnetism. We can reconstruct from marine magnetic anomalies how continents or plates move relative to each other, but how they are positioned relative to equator and pole, it relies entirely on paleomagnetism. And this is, it's not just fun. We're not doing this with our own paleomagnetic community, because this is the sole quantitative basis for all of our interpretations of paleoclimate, paleobiology, and in part plate tectonics. But particularly all of paleoclimate relies entirely on how we quantify the world for them. And what we are dealing with is we are all aware and we are all very careful in dealing with sources of uncertainty in our data. And we have three ways in which we can describe our uncertainty. We have scatter, we have error, and we have bias. Bias is undesired, and it's a problem. It's systematic. So, for instance, inclination shallowing gives a bias. All data are deflected from what they should be in one direction. And if we do not correct for that, we make a systematic error. Remagnetization is a bias. All of the data points are offset in a direction where they shouldn't be. So either we need to recognize and filter this, or we need to correct for it. Then we have error, which is undesired, but essentially random. So measuring errors, for instance, that we make around when we measure the orientation of a core that is oriented in a rock, that those errors will be essentially Gaussian distributed around the mean, and we can average those. And we have scatter, which is desired, and in the case of paleomagnetism, that is PSV, paleosecular variation. If we have a paleomagnetic data set that we collected from a bunch of rocks, then we want to see scatter. If we see no scatter, we haven't sampled the field that we wanted to sample, and therefore our result is unreliable. It still needs averaging, but it's not an error. It is something that should be there. And we deal with all of these issues in different ways. To overcome bias, for instance, we perform field tests and rock mag and microscopy just to see whether we might be dealing with, for instance, remagnetization. And if we convince ourselves that things are remagnetized, then either we have to adjust the age of our pole to the age of remagnetization, or we just remove the data from the data set that we want to use for paleogeography. We can correct for bias in the case of inclination shallowing correction. We have the EI method of Lisa, for instance, or the SVEI method, which is a recent update of that philosophy. And then we can correct for it and still, and in principle, propagate the uncertainties that are associated with those corrections and move on. There are other biases that worry me that we do not really correct for. For instance, we're all very fond of lavas if we want to collect poles, but lavas have, the last time I checked the volcano, it looked like this. So if we find a lava and we measure a bedding, we are not actually quite certain that that is a paleohorizontal. And that those biases we don't really take into account. We just put them horizontal and we move on. One thing that I learned is that we are very aware and very afraid, if I'm a little cynical, of our measuring error. And I understand that if we want to understand, for instance, if we want to reconstruct paleosecular variation, we want to reconstruct individual excursions of the field, then we should be worried about the measuring error that we make in our measurements. But if we are sampling, if we want to represent paleosecular variation, perhaps less so. What I was trained to do and what I've done for a very long time is that we go into the field and we find a lava and we take 7 samples. At least that was the lab where I did my PhD, was 7 samples. But other labs say, no, it should take 5 or it should take 10 or it should take 12 samples per spot reading, per lava, or per sedimentary bed. And then we should average those X number of measurements, because then we get rid of our measuring error, which is, depending on how bad your glasses are, about a degree, maybe 2. Right? This is an enormous amount of work. Enormous amount of work to double check every direction that we do 5, 6, 7, 8, 9, 10 times. Enormous amount of work to get rid of that 1 degree uncertainty. And we make quality criteria. I've done that myself for a very long time. We need at least 4 measurements for a spot reading, and K should be larger than 50 in a lava, and otherwise it's not a spot reading. But when we started to dig into the literature, there's actually no literature that shows that K is 50 as a spot reading. Yeah. You can also take K as 100 or 30 or 75. It's more or less arbitrary. I'll show you what the effects is of those filters. I've done field work with colleagues, and we did the same approach for sedimentary beds. Every sedimentary bed, we had to take 7 samples exactly in the same sedimentary horizon because we wanted to average our measuring error and then want to see what we want to make 1 spot reading for that 1 sedimentary bed. But you do not do that for a sedimentary bed. There is time in sediment, and it's almost impossible to have the exact same bed everywhere. Besides, a bed itself is an arbitrary thing. It has to do with 2 phases of non-deposition or slower deposition or whatever makes bedding. So it's not exactly known. You do not sample enough time for secular variation, but you also don't have a spot reading, so we don't really know what it is. And then for the corrections, for the bias, for the EI correction, we take sedimentary sections in which we explicitly assume that every reading that we get from the sediments is a spot reading, because we're going to compare the distribution of the data that we get from a set of samples with PSV10, which is a field model based on lavas, and we're going to see if that is the same. And if it's the same, then we say there's no inclination shallowing. So we are explicitly assuming, on the one hand, we're explicitly assuming that that we need to take 7 samples from a bed in order to get a spot reading. And on the other end, we're assuming that every reading is a spot reading itself. And then there's the elephant in the room, PSV, paleosecular variation. Paleosecular variation is, well, we use a 45-degree cutoff normally because PSV is about a circle with a radius of 22.5, right? So PSV scatter means that every individual spot reading that we take is somewhere between 20 to 25 degrees from the true spin axis of the Earth, or from the true dipole that we assume to align with it. This is the main source of uncertainty that determines the accuracy of our apparent pole. So this is what should worry us. And there's now quality criteria that we developed to see whether we actually have a scatter that represents PSV. And we made an attempt to do this conservatively in 2011 with Martijn Dene, whereby we used K values that had been reconstructed by PSV studies, anywhere between 12.5 and 50 or so, I believe we took. And we made a number. We made an envelope based on your A95 value that you get for a bunch of measurements that you take. If that is within that envelope, then in principle you might be looking at paleosecular variation alone. You have no reason to assume there's extra error or underrepresentation. Perhaps a more accurate test is the SVEI test that Lisa recently proposed, that tests whether a scatter that you get from a bunch of lavas or a bunch of sediments is in principle the same as the PSV10 database that is mostly lavas from the last 2 million years. It's officially the last 10, but most of them are from the last few million years. And then almost every paper that describes a paleomagnetic pole says we had PSV, and then we averaged it, and now it's averaged out. And I've never understood that, because it's not out. You've averaged it, but it's not out. You can't average something out. It's impossible. You can only average something. And the idea of statistics is that the more data you have, the smaller the uncertainty of your average. That's how statistics should work. But we don't do that. We say it's averaged out. So we take an average pole, and the error no longer matters. And then there's the final uncertainty, and that's age uncertainty. And also that propagates one way or another into our paleogeographic reconstructions. We have sedimentary data sets in which we estimate the age or the age uncertainty typically based on biostratigraphy. So we know that we're in the Aptian, and therefore we are, between 121 and 112 million years or so. That means that every data point that we collected in there could be somewhere in that age range. Whereas if we take a series of lavas, then we take an argon age of 1 or 2 of those lavas, and then we use that argon age as the uncertainty of the pole. But that's nonsense, of course, because it's the uncertainty of only one lava, and you have no idea what the lava on top of it is, unless you, right? So what we're going to get there now is that we have 2 sources, then we have 2 ages, but both ages mean something else entirely. Now, the way we traditionally make apparent polar wonder paths, and I co-authored them, and I was very happy with them. The way we traditionally make apparent polar wonder paths is that then we rotate all poles that we have on the planet into the coordinates of one reference plate, Africa normally, but it doesn't matter which one you take. And we start averaging them. We take every pole, every paleomagnetic pole, as a data point, irrespective of the amount of readings of the magnetic field that is behind that pole. We do not take the uncertainty, the location uncertainty of the pole into account. We don't take the amount of data into account. We take the average age, and we do not take the age range that the pole may have into account either. Then we average the paleomagnetic poles with a sliding window, let's say 20 million years or 10 or whatever you want. All poles with their average age within that window we're going to average. And then we have an average pole with an A95. That A95 that you see here, for instance, on the, can you see my, let me, highlighter here. No, that's laser pointer. This one I need, right? Every pole here with an uncertainty that you see, this does not mean the same as an A95 that you get around a series of lavas that you've, directions from lavas that you collected in the field. Because that A95 that you got from the field is a representation of PSV scatter. This here is a representation of pole scatter, whereby each pole is an arbitrary number of VGPs averaged. And you have no idea how many or what the uncertainty was. And then finally, we want to do tectonics with this, or paleolatitudinal displacements, right? Every week there's papers coming out showing how much the Himalaya has moved relative to Asia, or Tibetan blocks have moved relative to other Tibetan blocks. And we do that by taking, we take two poles, we calculate the distance between them, and then we compute the average as the square root of the A95 of the study pole squared plus the A95 of the reference pole squared. The A95 of the reference pole is ideally a bunch of readings of secular variation, and the A95 of the study pole is some mix of poles. And then from that, we say there is so much rotation, there's so much paleolatitudinal motion. And this is the central approach between the ongoing debates, some of them for decades, on whether there is a Pangea AB problem or whether there is a Jurassic monster polar shift, because it's based on these statistics. How do I move there? And then in 2019, I had a discussion, a heated debate about India-Asia. It doesn't really matter. I had a heated debate with Dave, and Dave sadly passed away 2 years ago, I believe. Because I've had long discussions with many of you and with many of my paleomagnetic colleagues, whether this all mattered, all this statistical nerdy mumbo jumbo. But Dave dropped a horrible bomb in 2019, because what he showed, to counter an argument I made in the tectonic interpretation, what he showed is that if we take that approach of calculating the distance between a study pole and an apparent polar wonder path with the A95 squared square root method, that 50% of the poles that were used to make the global apparent polar wonder path of Trond-Torsvik in 2012 are statistically significantly displaced relative to that apparent polar wonder path. In layman's terms, or in geological terms, what this means is that if you find a significant difference between a study pole and an apparent polar wonder path, you have a 50-50 chance that has a geological meaning, which is terrible. It basically means that paleomagnetism is useless. And what Dave suggested as a solution is that rather than using that A95, we use the envelope that encompasses 95% of the poles behind the apparent polar wonder path as the uncertainty measure. He called that a K95. And he showed that the K95 behind the apparent polar wonder path that we use to interpret almost every tectonics, all the tectonics in the Phanerozoic, is, well, here this in this image is 16 degrees, but often 20 degrees. It basically means that any motion within 2,000 kilometers latitude you cannot resolve with paleomagnetism, regardless of how well you have determined your pole. And this made it urgent to solve this problem. So Bram Vaas was going to write a thesis about something else entirely, but Dave's paper came out in the first week of Bram's PhD. And we decided to look into this first as a first paper, but it became the entire thesis. Poor man. And we tried to find out what the cause was of pole scatter behind the apparent polar wonder path. And the short answer is almost all of it has to do with the amount of data that are used to determine poles. It shall not be a surprise that poles that are based on small amounts of data are more scattered than the poles that are based on large amounts of data. That's the whole point of statistics. So the scatter and also the displacement. But scatter is primarily based on the number of data points used for a pole. And that number is completely arbitrary. The example is that in the apparent polar path that I co-authored in 2012, there are 8 poles of Deccan, which itself should give you poles, right? And why are there 8 poles of Deccan? There's only one Deccan. And those poles vary in the number of data points in lavas they used from 3 to 130. With the same ease, we could have made 1, 50, or 300 poles from the same Deccan lavas. And the outcome for the apparent polar path, for the uncertainty behind the apparent polar path, would be completely different. In other words, if we use poles as a basis, if we use an average of poles as a basis for paleogeography, then we end up with an apparent polar path with an arbitrary error that has 0 geological meaning. The only way we can get a unique and reproducible apparent polar path is if we use site level data, if we use the actual readings of the magnetic field. And there is no reason not to do that. Are there other sources of scatter? Well, yes, one mostly, and that is sediments that are not corrected for inclination shallowing, or that are corrected for inclination shallowing with, for instance, the assumption, a blanket assumption for flattening factor. Because it turns out there is not one flattening factor that applies to all sediments. So it's important to take the flattening, to take sediment. It's important to only take for global apparent polar paths to only take sediments that are corrected for inclination shallowing. This was a bit confrontational for many of us who made those apparent polar paths. Rob van der Voe, another great in our field, in 1990 came with the Q factor, came with his 7 quality criteria. And we've gone at length to determine for every single pole that we use in an apparent polar path what the quality factor was. And that is there rock mag? Is there a field test? Do we know the age? If we don't know the age, the rest of the quality factors don't really matter, do they? I mean, that we can't use it. And then K should be larger than 15, and N should be this, and A95 should be that. And what it showed is that the angular distance, so the scatter, the angular distance of poles with a quality factor of 3 relative to the reference, or 4, or 5, or 6 is identical. In other words, there's absolutely no correlation between the so-called quality factor and the scatter. The only thing, ironically, that we found is that only poles with a quality factor of 7, so the best poles according to the quality factor, are most scattered. So, okay, I made the point that it is important that we basically that we should go down to the VGPs if we want to make apparent polar paths. How to determine the VGPs then? If we would take one sample for every lava everywhere, and we would be blind to maybe lightning strikes, or to places where we were so tired and sweaty that we couldn't read our compass properly, or whatever uncertainties are in there. So is it important that we double check and triple check and quadruple check our own measurement every time, or does that really not matter? And to test that, Dieke Gerritsen, who just got her PhD with Stu a couple of months ago, in her master, she worked with Bram and with me to do an empirical analysis to see what difference it made to reproduce our own measurements time and again, and to do all those quality filters that we've been telling each other that we should do, otherwise the data are junk. And the one that I always used was the K cutoff. K has to be larger than 50, and otherwise we should not take the lava site into account. What we found is that in 4 big data sets that we had, 3 were from me and 1 was from Lisa. We found that there is no improvement at all in the eventual paleomagnetic pole if we take a K cutoff of, the only thing that a K cutoff does is decrease number of sites that we use. And the result is that the A95 of a final pole increases. That's the only thing it does. It decreases n and therefore increases uncertainty. Here we did a test. We calculated the average paleomagnetic pole if we took only 1 sample from every lava and then compared it to NS6. And there's zero difference. There's zero difference. There's absolutely no improvement of the final pole if we take NS1 or NS6. When I saw this, I was a bit upset. I thought, I've been wasting my time taking 7 samples per lava. And if I would have taken 1, I would have gotten perhaps a somewhat larger scatter, but I would have ended up with with a larger n, so a lot smaller A95, and the same, within any form of error, the same average. So every filter that we've tested decreases the number of data points, increases the A95, and do not significantly change pole position. So the only thing that we should be worried about, apart from bias is a problem, right? Inclination shallowing is a problem. But the only thing for the rest that we should be worried about is how many data we can get to represent PSV. And this was reiterated in a more mathematical approach of a paper in Sapienza, and Matt Domeyer and Nick were involved a year later. So the analogy that I've given this presentation to my students earlier this week, and the analogy that I've given them is if we as a bunch of paleomagnetists, me included, go into a cinema and we want to know the average age of the people in the cinema, then we take a very small selection of people per row, and we ask them their age 5 to 12 times, because we're very worried that there might be a few people who can remember their age. And then we filter anyone who didn't answer more than 3 times, for instance, and we average the answers, then we average the rows, and then we average the averages of the rows. And then we don't publish our data, but only the statistical descriptions of them. Whereas what we should be doing is simply ask as many different people as we can find for their age, average those, and the more we ask, the more data we get, the better the average, period. So we want to build APWPs from site level data. I would like to propagate all uncertainties because we ignore all of them right now. And then the last part, and that is the part that is new and actually not done yet, is to improve age resolution. And I think to do that, we need to essentially start over, because if we want to improve age resolution, we need to do this from the original paleomagnetic readings upward in a stratigraphic context. And because 99%, I think, of the published paleomagnetic legacy data, we do not have the original directions, we cannot use them. And because that is a big problem. We need to go down to site level, yet almost no one, even to this date, publishes the data. We have magic, there are data and magic. We made our own, we made paleomagnetism.org as a tool, and there we can also publish our data. And it's critical that we put our data in these databases. But even to this day, we all know 9 out of 10 times it doesn't happen. Right? What is publishing data means that you get an Excel sheet with interpreted directions, but that is not the data. So what we need to do if we want to go down to site level data is, since we don't have them, we have to do a trick. And the trick that Bram came up with, he didn't come up with parametric sampling, but we tried parametric sampling. So basically we let a computer draw n number of data with from a statistical distribution with some k value. And we tested with PSV10 if we would take the let's say the poles that were used to make PSV10, and we parametrically resample those, we get a distribution of ages that conservatively approximates the real distribution. We get a scatter that's a bit larger than the real PSV10. So as a quick fix approximation, we could do this. And then we compiled the global apparent polar wonder path. And we have now made the first update of that, which is in review in +1. While the update is part of a reconstruction, much larger reconstruction paper. But that means that we have now 15,000 VGPs. And that sounds like a lot because it was 385 poles. But 15,000 VGPs is virtually nothing. This is 15,000 paleomagnetic directions since the Carboniferous that constrains all of paleogeography and everything that is built on it. Yeah, if you take a magnetostratigraphy, our Chinese colleagues have these very long magnetostratigraphies in the foreland of Tibet, right? That go from 50 to 10 million years or so. They've got, in one section, they've got more samples than we have globally to constrain all of paleogeography. So this is actually very little. This database we will update until we have something better. We will update this, and we do that every 2 years or so. So the latest version is GapWeb 25, which is on the websites that I indicated earlier. The database is on apwponline.org if you want to see it. And then we try to propagate at least the age uncertainty into the apparent polar wonder path. And we did that in the following way. From a paleopole with an n number of data, in this case, let's say 7, and some age range, whereby this age range, as I indicated in the beginning, might either be a stratigraphic range or an uncertainty of a uranium lead age or whatever we gave, which is a worry, but okay, this is what we did. From this interval, we randomly draw 7 directions that together make the statistical distribution that was published. And every individual direction, we assign a random age within the age range. And we do that for all poles. And then if we want to compute a paleomagnetic pole, we choose a center age of a window and a lower and an upper age bound, and all individual directions that fall within that window are then averaged to make one pole. And then we iterate in a bootstrap way, right? So we do this again. You again draw the numbers, you again assign ages, and the next time, all of these directions are going to be a little bit different. Some of them are now outside of our window, some of them will be in. And you do it again. And this way we end up with let's say 1,000 paleomagnetic poles, and then Bram chose a 95% circle that encompasses 95% of those poles, and consider that the uncertainty of the average paleopole. And this way we are working on site level with these pseudo VGPs that are not real, that are resampled, and that take the age uncertainty into account. And the apparent polar wonder path that we got, so this is the first iteration. You see in white, you see the version of 2023, and in colored numbers, you see the new one. So you see small differences, which are to be expected if you add data. And then in vague, behind, you see Trans 2012 apparent polar wonder path. We were happy to see that at least we reproduced that path, right? If that would have been totally different, we would have had a problem. But there are differences here in the Jurassic, here in the Triassic. There are differences. Even here in the young history, there are differences. And the biggest difference is that the uncertainties have decreased significantly, which is to be expected if you go from 300 to 15,000 data points. Now, one thing that is clear is that the number of readings that we have per time interval of 10 million years varies dramatically. I think Jean Besse and Vincent Cotillot already called an apparent polar wonder path a large igneous province path, because it's very much focused on where we have large igneous provinces. But one thing that should give you pause is that here in the late Jurassic, which is the center stage for the big ongoing discussions on the monster polar shift, our global apparent polar wonder path is based on maybe 100 directions, right? Any magnetostratigraphy that tries to accomplish 3 crons has more directions than we have globally for the Jurassic. So, and it's in a hyper-reversing field. So if we have very spectacular motions in a time interval where we have very few data, then maybe we should double check whether the interpretations, triple check those interpretations. Now back to Dave Rowley's problem. Did we now solve that problem? Because that's what I set out to solve, right? We call that circle that encompasses 95% of the bootstrap poles, we call that the P95, which is even smaller than the A95 of the old apparent polar wonder paths. So it doesn't take much for a pole behind the apparent polar wonder path to be significantly displaced. And the solution that we found is to weight the reference pole against the amount of data that we used for a study pole. So suppose that you went into the field and you collected a pole based on, in this case, N is 15. Okay, you had 15 lava somewhere and you wanted to know whether, or 15 sediments, or whatever, and you wanted to know if there's a rotation. Then instead of comparing that to the reference pole with this very small P95 that is based on 1200 directions, we resample from that distribution only 15 directions. And you do that 1,000 times, and then you get a much larger scatter, of course, because now, and then we get the same reference pole, but with a much larger uncertainty. And that uncertainty is the reference pole if we would have made it from the same amount of data as our study pole. And what we showed in Bram's paper in 2023 is that this way, 95% of the data behind the apparent polar wonder path are not statistically significantly displaced to the apparent polar wonder path, meaning that if you find a difference, you have a 95% certainty that you do something geologically meaningful. And then we made APWPonline.org, where all these statistics run behind on the background, and you can use it for your calculations. Now, the final part is I'm actually not quite happy yet. And the reason is that now we have taken PSV scatter into account, but we still have a terrible age resolution. If we would have made, so our apparent polar wonder paths currently run with a 20 million year window in which there are poles that overlap with the edges. So we are averaging something on the 20 million year timescale, which means that any variations in between that, like the polar shift, are very challenging to reconstruct. I think this was the point that Giovanni Mottoni already made in 2005, right? How can we, there might be spikes in there that we average by smoothing that age. So how do we deal with that? And we can deal with that, but that's going to take a lot of time and a lot of effort. Is that worth it? Well, just to give you a small example of why it's worth it. We've actually done the same thing in marine geophysics. We know that there is, from the magnetostratigraphic timescale, we know there's a whole bunch of reversals, right? When we make reconstructions of the ocean floor, we're not using all the reversals. We're using a reversal every 5 or 10 million years because plate tectonics doesn't change quickly. Why would you why would you go through the effort of picking every reversal, which is one hell of a job? So we don't. Until Chuck de Metz did in 2021 with Merkuriev using legacy Soviet data for India. And what they showed is that when India was racing towards Eurasia at an average rate of something like 18 centimeters per year, according to their data, when they picked every million year, they saw variations in the convergence rate that varied by more than 10 centimeter per year on a 2 million year timescale. Well, is that crazy? Or is it a signal? My PhD student, Erik van der Wiel, and Jakub Pokorny, a PhD student from the Czech Republic, were aware of this data set of Chuck, and then they looked in Jakub's numerical models. And in those numerical models, Jakub was trying to figure out how slabs enter the lower mantle. And because slabs in the upper mantle sink much faster than the lower mantle, so they have to thicken. And what Jakub was working on is how that buckling of slabs goes. And what he saw in his models is that when slab buckles forward, plate convergence decreased and then rapidly increased as it rolled back and forward and rapid. So what they argued is that we might be looking in these rapid fluctuations, we might be looking at a real signal of plate model, regardless of whether you believe this hypothesis or not. This is we can have a discussion about that. But one of the things that Eric showed in that paper is that if we take the magnetic anomalies every 10 million years as we've done, we are blind to any such variations that might actually be real. And I think that if we would go to a much higher resolution in paleomagnetism of not 20 million years, but 10 or 5 or 1 million year, then we might find a whole series of unexpected results. So suppose that we wanted to do that, how would we do that? I think that where we have to go to is to a similar situation as what the paleoclimatologists have done. If we would do paleoclimatology the way we've done paleomagnetism, we would be unaware of an early Eocene climate optimum or a PETM or an Eocene-Oligocene transition or a KT boundary. We would have never spotted them, right? We would say, well, this is high and then this is lower and this is lower in 3 steps and we're done. The way they've built this is by assigning an individual sample in a very long, in this case, often drill core. We can't use drill cores because we need to know declination. But in these drill cores, there is integrated stratigraphy, MagStrat, cyclostrat, biostrat, you name it, tephra-strat if it's possible. You make an age model and every individual sample is assigned one age. And then we assign to that age, in the case of climate, we assign it some isotope value. But for paleomagnetism, we can give it a paleomagnetic direction. And that direction has an MAD, as a maximum angular deviation error. And we can propagate the uncertainties of an inclination shallowing correction that you do with sliding windows or so over your core. You can propagate those in there. And perhaps there are other sources of error that we can all break down to the uncertainty around one single direction. And if we do that for very long sections, then we're not talking about 15,000 directions per Phanerozoic. Then we're talking about 15,000 directions for the early Eocene. And you do that for different sections. You can rotate and stack those data. And what you then end up with is super high resolution paleomagnetic records in which the highest variation will be constrained by the time intervals where we have most data, which is the way statistics should work. So I think this is the way we should go. And that means that all of you who have done magnetostratigraphy in stable plate interiors, please, please, please make all of your data available. Not just the directions, just make everything available, because this is the way I think we move forward. And I can see many, many different ways in which this is going to be difficult, right? Because for some intervals, here if you go to the Jurassic hothouse, everything is limestone. Good luck. There's a reason we only have 100 directions from the Jurassic. But I think this is the way forward. And what this also means is that essentially lavas are useless. Because lavas give us very nice paleomagnetic directions, but they're almost impossible to date unless they are in a section where we know sedimentation rate or where they fall in a precession cycle. But for the rest, lavas will never give us high resolution ages other than what we get from one individual argon age of one individual lava. So I think this is the way to go. We should definitely abandon paleomagnetic poles as a hierarchical statistical level. And we should always go down to side level APWPs. I think that with the high resolution, we will drastically improve paleogeographic precision, and it is right. It's always questionable whether that is going to make a difference. But given that everywhere where we went to higher resolution, we learned very interesting stuff. For instance, high resolution apparent true polar wonder and high resolution true or high frequency true polar wonder. We've had this discussion in our community now for a while, but the geodynamic consequences of, for instance, such a Jurassic polar shift are enormous. The only way to have a Jurassic monster shift back and forth is if mantle convection in that time went suddenly tenfold faster than in any time before or after. Right? This is where you're talking essentially about a huge mantle overturning in no time. That is not just a paleomagnetic hobby. That is first order geodynamic news. Apart from all the climatic consequences that something like that might have. And finally, whatever we do, please, please, please publish. Let's make sure that all of our data are published for future generations who will hopefully be smarter than we are. Thank you very much.
Okay, thank you, Douwe. And it was a good 25/50 minutes talk.
Yeah.
But it was very interesting. Thank you. Thank you.
I didn't have a clock.
That's fine. We couldn't stop you. It was really interesting. Now maybe we have some time for questions if somebody has any.
Sarah?
Okay. I don't have questions. I have a bunch of comments. Thank you so much for this presentation. I've been following your work and Bram's work since he started because I used to work with APWP in my early research and stuff that I never published right there in that Jurassic sweet spot. So every time I listen to your presentations, I'm like, I really should do that. Eventually I will. And so I have a couple of comments about, for example, the age error. One thing about the age error that has also to be taken into account is if magnetostratigraphy was used to constrain the age, which is what basically I was doing back at the time. You really need to be careful on which magnetostratigraphic scale has been used because in some intervals that would give a significant error, significant difference. And a problem that I was encountering in my case, I was studying a stratigraphic section, okay, across the Jurassic. So was the elongation inclination because, of course, you have to be careful not to use that because it really depends if you're going across different formations, so different lithologies, the elongation inclination will change. And also, when you average the elongation inclination, you are basically supposed to average across strata, same age. But you cannot really average if you are doing a stratigraphic section because otherwise you risk to average out what is a real plate motion. I'm not sure if you understand what I mean. You see what I mean. So also, I'm not a volcanologist, but volcanoes are not all like this. So I guess that is also a case by case scenario. But I really love the site level approach. And the final idea that you were showing of doing, using all the data. So yeah, I mean, thank you for your work. I'm really looking forward to the final results.
Thank you very much, Sarah.
You want to comment, or Nick?
Well, obviously, lots of the things that Sarah said, I fully agree with. The difficulty is that you do not what you want to. Well, for instance, in it by taking the EI correction is going to integrate time and integrate stratigraphy. So obviously there will be lithological changes. If you start averaging 10 million years, then plate motion might be significant. Rotation, that's one of the things that Stu, I think, has already worked on. That if you have rotation in your section during deposition, then obviously you're going to create an elongation that has nothing to do with inclination shallowing. So there are many different ways. It's actually quite difficult what we do. We have quite a difficult task to get to our final answer. So I'm aware of the pitfalls that Sarah indicated. I also think that obviously the assumption that lavas are horizontal has worked pretty well for many of us. But it's just that every time I see a lava flow out, I think that's not horizontal. So if you take lavas across a large region somewhere, let's say many square kilometers, then it may average out. If you take a section like I did in Mongolia, take a section and you measure the bedding, then there might be a bias involved. So, it is what it is. We do the best we can with lavas. I understand why we took lavas, but I also start to see lots of pitfalls with them. I think Nick was first.
Yes, Nick.
Sorry, Anita, you want to do this?
No, it's fine. Thanks.
I really think this site level approach, when I first saw it, that it was a great way of going forward. I was wondering, I mean, dating lavas has become a lot more precise over the years. I was just thinking of like what sort of uncertainties on the ages, 100,000 years or 500,000, like what becomes like where that uncertainty is less than the pole uncertainties.
I think that the problem of the uncertainty of the lava, we may date the lava very precisely, but that is in one spot reading. So, for instance, I went to Mongolia where I took a whole bunch of lavas in the superchrom, and we took 80 or so, and then we dated 2. So, what's the age of my pole now?
You date the top and the bottom.
Yeah, and then I get an age. So we did that, and then you get an age somewhere between 126 and 118, right?
Yeah,
and that's fine.
Yeah, I mean, if the lavas are spreaded that far, then yeah, you need to do a lot of dates. That's true.
So if we want to go to this stacking of section approach that the climatologists do, then these lavas, we can't do that. With lavas, we cannot go to a higher age resolution than what we do now.
Yeah,
and in
you
many
need to
cases,
date
we're not actually
a lot of
taking
flows.
Huh?
You'd have to date a lot of flows to.
You have to date a lot of flows, and even then you have a bunch of spots where you know an age. And if you have a section, then you can say, well, that's the top, that's the bottom. But often that's not how it works. You go into the field and you collect in a region a bunch of lavas, and you do not really have stratigraphic control. So okay, we're roughly in this few million years, which were the approaches that we had so far worked fine. But if you want to go to higher resolution, then I cannot think of a way of going beyond that resolution.
Unless you can easily and cheaply date every lava that you sample, basically.
Yeah, which is time consuming and very expensive.
Yeah, it's difficult and expensive. Okay, thanks.
Thanks, Gary. And then there are 3 questions in the chat.
Well, I agree with the sentiment of the others that using VGPs from site level is a nice addition. I just want to comment on the rally problem because I think there's a confusion between using a standard error and a standard deviation there because, for instance, you were saying that very few of the poles fall within the alpha 95 of the mean. If you were to measure the length of your desktop, for instance, and you did it 100 times, only 7 of those measurements would fall within one standard deviation, and 2 standard deviations is about 95% confidence limit. So about 14 of those 100 would fall within your 95% confidence limits. So you basically, for standard error and for alpha 95, you're dividing by the square root of the observations, and therefore the number of observations that fall within the uncertainty limit are much, much smaller than if you use the standard deviation, which is kind of what Raleigh was doing by saying, well, if we just make the alpha 95 not an alpha 95 anymore, but make it large enough to encompass more than 50% of the poles, now you're not actually using the 95% confidence limits.
No, and I understand that part. In principle, it is for the approximate. If you wanted to use the average pole to constrain, let's say, the paleolatitude of India for some animal that you find there, then it doesn't really matter how many poles fall outside it. But what I think Dave indicated that is really a problem is that in principle, if we compute the distance of a pole that we use to calculate the apparent polar wonder path from, and we compute the distance of that pole with its uncertainty to the apparent polar wonder path with its uncertainty, and more than half is statistically significantly displaced, then it means that we cannot use that measure to determine whether we have a tectonic rotation or not, because clearly those poles should not be rotated relative to the apparent polar wonder path. We said that they came from the stable plate interior. So it was and he used it to argue. I had made a point that there was paleolatitudinal motion of some block relative to another block, and he said you can't say that because 50% of the poles would give you that displacement, even though we all agree that it didn't happen. And that's what triggered me. And that's what, at least now, we no longer have.
Yeah, I'm just saying a more conservative alpha 95 or uncertainty as it is fine, because I think what you see is there are a lot of systematic biases in the data. And when we built the Parent-Polar Wonder Paths, kind of in my dissertation and stuff, we added systematic errors for things like if you got the data from a ODP drill hole, well, those drill holes are rarely perfectly vertical, so they're a couple degrees off. So you add that in. You add biases for not averaging secular variation and so on. So I agree that the real uncertainty is probably larger than the alpha 95, but the observation that not many of the not many of the poles fall within the alpha 95 is actually something you expect statistically. So
Mhm.
If
Yeah.
if I can comment on that. No, but that's completely true. But I think that how I interpret Rowley's main point is that we then compare the uncertainty of an individual pole to this uncertainty on the mean, which is comparing apples and oranges. Because you indeed expect individual study poles to fall outside of the mean of this APWP pole, if I can call it like that. But I guess what we try to add is that you can then really increase the uncertainty on the parent-polar wonder path by just looking at the 95% envelope that contains all the input study poles. But then you weight every pole equally, right? So as Douwe pointed out, they have vastly different number of sites on which they are based. So that is I guess the new thing that we brought into the discussion to really look at what does the individual study pole mean and on how much data is it actually based.
Thanks, Bob. There were questions in the chat, and I don't see it.
Yes, there was a question from Diego, but I asked to clarify. I'm not sure I understood the question. So the question was, do you think that using real site data would increase the resolution of the apparent polar wonder path, or would it be an unnecessary effort? I asked Diego what it means, real site data.
Yeah, but I think I understand what he means because
Okay, thanks.
Bram makes up his data points, right? We make pseudo VGPs, so we do not have the real data that were used to calculate the poles from. We randomly draw them. There is a study that Leandro Gaggio has done. When was it, Bram? 23 in GRL with a whole bunch of people, in which they computed they collected the real VGPs, the real site data from lavas of North America, which was, I think, weeks of work for a whole team of people. And then, because you know stratigraphic order in those site level data as well, they could compute an apparent polar wonder path from the real data. And that, yes, that made a difference. And it was a very nice, smooth path, if I remember correctly. So yes, I think that will make a difference. In principle, if we would have a lot of time and patience, and you would calculate, you would collect data from in high resolution throughout a stratigraphy, you're going to find secular variation, right? This is how we found the Blake event, or for instance, a couple of years ago, 10 years ago now, 15, getting old. In a section in Germany, there was a sedimentary section, and you see gradually you can find those traces. So will that matter? I think using real data and having real data with real uncertainty rotated into one common reference, whereby you stack all the data from different sections, I think is going to make a huge difference. The question is what difference it'll make for instance, interpretation of climate or plate tectonics or true polar wonder. I don't know. We will only know if we do it. But I think it's always better to use real data instead of artificially resample data from some distribution, whereby we assume that the distribution was Fisherian, knowing that it probably wasn't. So I think that'll make a difference. But it's going to be, so the way I'm looking at this is that if you were looking for something to do in the next 20 years, here you go. Write your proposal. I'm going to try. If you see a proposal like this landing on your desk, please be nice. One can and should get ages, said Nick, from multiple flows in a lava stack. That is, I think, what you already said out loud.
There was a question of a reference database to offer high resolution paleomagnetic data from shallow water carbonate Cretaceous in age. As a specific question from Marina.
Well, we have magic, of course. And we have our database of paleomagnetism. Oh, that's one thing that I needed to say. One thing that remind me that I add that. So that is where where those data can be published. But with those reference databases, with those high resolution PMAG data from a shallow from a magnetic stratigraphy, drop me an email because we're looking for stuff like this, right? Let's see what we can do with it. And one thing that I wanted to say is one reason I think that we are not sharing our lab data much, apart from, I mean, probably everybody here is nicely putting all their stuff in Magic, and I'm yelling at you for nothing. But one of the big problems that we face, of course, is that each and every one of our labs is using their own data format. And in my little hobby tool, paleomagnetism.org, you can upload all those different formats, but now we have a programmer in our department who has been so friendly in the last year to make a converter from every paleomagnetic data format into any other paleomagnetic data format. It'll come out in the next weeks. I'll drop an email around on the GPMag list. But in principle, you can now share data between lab formats and do it all in your own pet environment that you want to work in. You can, in principle, see all data of everybody else. But I'll email that a bit later.
Okay, thank you. I think we are running even over time, but it was really, really interesting. If you can please unshare that, I will share my screen for one last slide. And please, everybody, a big round of applause again to Douwe and the huge amount of work there.
I was just talking, right?
Okay, so this video and the past ones, you can still find them on the YouTube. And our next speakers are 18th of March, Nelly Giordanova, and on the 8th of April, Elisa Pispa. So I will invite you to join and sign up on the YouTube channel, and I hope you have access to the mailing list. If not, please let us know. So thank you for coming.